Hello, welcome. Today let's try to solve Leetcode problem 310, minimum hit trace. So we are given a number n, means the number of nodes, and also edges, it means the edges for the tree. So we want to return the node with the minimum depth of the tree. So for example, for the structure 1, 0, 1, 2, 1, 3 for the edges, so the minimum depth is for node 1. As you can see, for node 1, the depth is 1, and also for others, the depth is always 1. If it is node 2, so you're gonna say if it is the root, so the depth will be 2, because 2, 1, 0, 2, 1, 3 will both be 2. Yeah, so we are sure it should be not 1. And let's see another example. For n equals to 6, and we have edges like that, and the node should be 3 and 4, because for 3 and 4, the depth would be 2. As you can see, for 3, 3, 4, 5. So the depth is 2. And for this 4, 4, 3, 1, or 2, or 0, it is still depth of 2. So we're going to return a node of 3 and 4. Now let's analyze the number of nodes. So it will be 10 to the power of 4, and the edges will also be 10 to the power of 4. It means we cannot solve it by brute force. So this is what I try to solve it in brute force at first. Yeah. So for the brute force, we're gonna enumerate each node, and for each node, we're gonna calculate the depth. And for calculating the depth of a tree, it will be easier. We just need to build the graph first, and then we can use the DFS to check the depth of the tree. Because this is not a binary tree, so it may have too many nodes. For example, for node 3, it may have too many nodes. So we can use the DFS to search the depth. Yeah. So yeah, the first line is if G node. So if there's no child, so I'm gonna return a 0 because I'm going to calculate the depth. So from the beginning, result is 0, and then I'm going to check all the neighbors. So if neighbor is not equal to parent, yeah, so this is parent is like a visited set. Yeah, it means I cannot go back. So the result would be from the beginning to the DFS neighbor with my current node. So for example, for this 3, the parent I gonna define a -1. So for this 3, it cannot go back, but for its neighbor, it's gonna have a 0, 1, 2, or 4. Yeah, and then I'm going to get the maximum result. So the depth will be 2. So I gonna return a 2 for this one. And yeah, so this is what I get the depth. After I get the depth, so I'm gonna prepare a result array and enumerate each of the node, and then I get the minimum node. It's the minimum number, and then I'm gonna check inside the result array which one is my minimum number, and then return the result. Yeah, maybe you also try to solve it like this way, and you find that you cannot pass it for Leetcode. Let's just try. Yeah, it's gonna take some time because it will be time limit exceeded, because 10 to the power of 8 it is not possible. You can see it passed 65 testing cases out of 71. You might think we can also use a case. Yeah, but for case, the time complexity will still be 10 to the power of 8 n square. Yeah, it will not pass. Yeah, because even if you use case, for each of the node, you have to check all the conditions. Yeah, so basically you cannot reduce the time. Yeah, as you can see, it passed 69, but it cannot pass for all the testing cases. It means this method is not okay for such problem. So for this problem, we're gonna try to use some graph method to solve the problem. Basically, we can analyze the graph like this. Yeah, if we have a structure like this, if we can take out the node one by one, what's gonna be left behind for the structure? Yeah. So for example, we have a structure for the first one. We have a structure like this. What if we can take out the node one by one? And how can we take out the node? Yeah. So we are going to calculate the minimum depth of the node. So can we find the node which is the minimum depth? Can we directly find the node? Yeah. Yes, we can, because the node will always appear in the longest path. So for example, I have like 3 nodes. There is only one path, and the node must in between, in the middle of this path. So for example, for this one, for example, we have a node 1, 0, and 2. So the node would be 0. Yeah, because the longest path is 2 and 0 is in between, in the middle. So we're gonna have a 0. So what about if there are 4 nodes? So this is maybe 3. Yeah, and this is 3. So in between, in the middle, it's gonna be 0 and 2. So we're gonna return 0 and 2. Yeah, because for 0, the depth is 2, and for this 2, the depth is also 2. Yeah, but for node 1, the depth is 3, and for node 3, the depth is also 3. Yeah, so by this analyze, by this by analyzing like this way, so for finding the node for the minimum depth of the tree, basically we're gonna find the longest root first, and then find the node in the middle. Yeah, for example, if there are more nodes, like this kind of structure. So we have a more node, like here we have 3 nodes, and here we have another node, and here we have some other node. Yeah. So the final root we need to find, it should always be the longest root. So for example, this is 1, 2, 3, 4, and 5, and this is 1, 2, 3, and 4. So it must be in the longest path. It must be in 5, in this path. And then in this path, we're gonna find 2 nodes in between, in the middle. So it is this one and this one. Yeah. Now let's check if those 2 nodes are what we are going to check for the minimum depth. So for this one, the minimum depth is from here, 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 and here. It is 3. And what about this node? The minimum depth is also 3, because here, this one is the longest. It's also 3. So it means that those 2 nodes are what we need to get for the result. Yeah, we can prove it by preparing some examples. So it means what we left behind for the node, it must be 1 or 2 nodes. It cannot be more than 2 nodes. If it is 3, let's just try an example. What left behind for the final node is going to be something like this. Yeah, if we left behind 3, it means we can still take those 2 nodes. It means we left by 1. So if we left behind 4 nodes, like this one, we can still take out 2 nodes. So what left behind is 0 and 2. Yeah, so it means the final result must be 1 or 2 nodes if it exists. If there's only 1 node, it doesn't exist. Yeah, so what we're gonna return? So we just need to return this node. Yeah, and according to the definition, if there's only 1 node, it should be not 0. So we just need to return an array of 0. Yeah, so now we can solve it by this way. If we can solve it to calculate the left node, what left behind, it may be 1 or 2. Now we can use the topological sort to solve the problem. Yeah, so for this structure, 0 is in the middle, in the center, and then we have 0, 2, and 4. We can use a topological sort to solve it. First of all, we're going to put the degrees of 1, because 0, 2, and 3, it is the leaf node. Yeah, if it is the leaf node, we call it a leaf node of a tree structure graph. Actually, this is a graph. Yeah, if this degree is only 1, we're gonna take out this 2, take out this 3, take out 0 inside the queue. So what left behind is only 1. Yeah. So if the number of nodes left behind is less than, if it is less than 3, it means 1 is less than 3. We're gonna return this node 1. Yeah. So for example, there are 4 nodes. We're gonna first put this node 1 and this node 3 inside the queue, according to the topological sort algorithm, because the degree is 1. And then we're gonna take this out and take this out. Now what left behind? Because there are only 2 nodes left behind, so we're gonna return this 0 and 2. Yeah, so we're gonna always check the numbers of the node left behind. If left behind is less than 3, so we're gonna return the result. Yeah. If there's only 1 node, like the node 0, we just need to return this node 0. Yeah. Now let's go back to the code editor to finish the coding. So we cannot solve it like the brute force way. We have to use some algorithm clever enough to let the time reduced. So by using topological sort, we just need to use use ON time complexity, because we're gonna basically use the BFS to check the check all the nodes, and we're gonna use it by only once, and then we find the result. Yeah. Now let's try to prepare the topological sort for the problem. Yeah. Now we're gonna prepare a graph and we're gonna prepare a degree. So the degree gonna be from the 0 times the number of nodes n, and this is for preparing the graph. So while preparing the graph, we can also prepare the degree. So the degree u should plus equal to 1, and the degree with v should plus equal to 1. Yeah. And here, this is for preparing an adjacency list. You can also use a default dicta set, but I think the list is much more faster because there's no duplicate node inside the adjacency list. Now we're gonna prepare a queue for the topological sort. So for the queue, we're gonna prepare a list because the final result would be a list. You can also prepare a dequeue, but you need to turn this dequeue into a list. So I'm gonna prepare a list directly because basically I don't need to use the queue structure. I can also use a list. So I'm gonna take the degrees of 1 inside my queue at first. Yeah. So I'm gonna use the queue for id in enumerate the degree. So if the degree equal to 1. Yeah. And now I'm gonna check the left node. From the beginning, my left node will be n because I have a number of n nodes. Yeah, so this will be the left node. It will be n from the beginning. Now I'm going to use the topological sort. So while the left node is more than 2, it means I can take out the node when the degree is only 1. So I'm going to have I'm going to loop through the queue. So for node in queue, and I find a node, and then I'm gonna find the neighbor of the node. Yeah. So for neighbor in G node. Yeah, but before that, I'm going to prepare. But before that, I'm going to minus the node. Yeah, because inside the queue, for example, for this example, we're gonna have 3 nodes, 0, 2, and 3. So we're gonna check the left node first. So the left node should minus the length of the queue. Now we are going to loop through the node. So for node inside the queue, and then we're gonna check the neighbor. So if neighbor is also, if there is a neighbor inside this node, for example, this is a node 0, the neighbor is 1. What I'm gonna do is First of all, I'm going to check the degree because this is the BFS topological sort. I'm going to check this degree. If the degree neighbor should minus 1, and then I'm going to check the degree with this neighbor. If it is equal to 1, I'm gonna put it inside the queue. Why? Because for this one, from the beginning, the degree is 3, and then I'm gonna reduce 1 by 1 until it is 1. I'm going to put it inside the degree. Yeah. But for this example, the left node, if it is less than 2, I gonna go out of the loop and return my queue. Now I'm gonna put it inside a new array because I'm gonna use this queue as my length, as my count, to count the number of the node. So I'm gonna to prepare a temp array to put the node inside. Yeah. So if the degree is 1, my temp array should append this neighbor. Finally, I'm going to give my temp array to this queue because for the while loop, I'm going to check next. Yeah, so it means, I'm gonna take out the leaves 1 by 1 until there's only 1 or 2 nodes left behind, and then I'm gonna return the queue. So queue should equal to the temp. Finally, I'm gonna return this queue. So if the queue exists, else there is only 1 node, I'm gonna return 0 because the number of nodes will be at least 1. Yeah. Now let me check if there's anything else. Yes, first of all, this is a queue. I'm gonna prepare the node inside if it is the degree equal to 1, and then I'm check the left node. If it is more than 2, I'm always use the BFS to check. Yeah. So the left node left behind and temp, and then I'm gonna prepare a temp array, and then inside the queue, I check each node inside the queue and check its neighbors, the degree minus 1, and if degree equal to 1, I'm gonna put it inside. Yeah. Why it works? Normally for the BFS we use a visited set, but for topological sort we don't need to use that because it can never go back. So for example, this node from beginning, if it is 0, it go to 1, right? But this 1 can never go back because if it were to go back, the degree should minus 1. From the beginning, it is 1 for this. Let me check. Yeah, if it were to go back, the degree would minus 1. For this 0, from beginning, the degree is 1. If it minus 1, what's gonna happen? Yeah, it's gonna become 0. But we only check the degree equal to 1. So it means it can never go back. So this is why the topological sort works. Now let me run it to check if it can pass for the testing cases. As you can see, it works. Yeah. Now let me submit it to check if it can pass all the testing cases. As you can see, it passed all the testing cases and it's much faster, and yeah, it works. Now let's analyze a little bit about the time complexity and space complexity. We did actually use a queue structure. It is a list. So that is a ON for the space. And for the time, while we are using the while loop, actually it is a BFS. We just go through each of the node and with its edges. So the time complexity is O E plus V. E is the number of edges. V is the number of vertices.